So here we have question 1 of version J of the 2025 AP Physics 1 exam. You can read it for yourself. They've been available online for a little bit now. So take a moment to read that. And so now we're going to get started with our solving this question. So you can see I'm told all about my cart here. Cart is dropped, or excuse me, a block is dropped onto the cart, and then the cart continues to roll. You should read this more in detail. So on the axis below, it's asking us to sketch a graph of the momentum in the x direction. That's what that P sub x means, of the x component of the momentum of the block cart system as a function of time. So if we think about what changes the momentum of a system, well, the only thing that can change the momentum of a system is a force on the system, a net external force on the system. So if I think about this cart block system, are there any net external forces in this horizontal or x direction? Well, the answer is there aren't any. And so even when this block collides at time t equals t1, we're going to end up with no change in that the cart block system's momentum. So my graph is going to look something like this. It should be a straight line all the way across, even after the cart and the block collide. So I should have a straight line all the way across. Let me see if I can draw a better straight line than that. Close enough. And so as long as it's straight, there's no change. It doesn't look something like this. There's no loss of momentum when the two blocks collide. So let's go on to part 2A2. I'm right up here. I'm finding an expression for the speed of the cart after time t equals t2 in terms of mc, vc, and the physical constants as appropriate. So let's do that right here. I have to begin my derivation by writing a fundamental physics principle or an equation from the reference information. So what I want to start with is conservation of momentum, and that's going to be this. It's going to be the mass of the cart times the velocity of the cart before the collision is going to be equal to the total mass after the collision, which is going to be mc plus 1/5 m sub c times whatever the velocity is afterwards. So it's going to look something like this. This is the momentum before, and this is the momentum after. So both of these are the expression for the momentum before and momentum after. And notice I'm doing it in terms of the variables that I'm given. I'm doing it in terms of MC and VC. And so now the next step that I need to do is I just need to get VF by itself. And so the way that I'm going to do that is by dividing by this term right here, MC plus 1/5 MC. And so these two terms are going to cancel each other out. Just like this. I'm going to do the same thing on both sides. MC plus 1/5 MC. And so my final equation is going to look like this. It's going to look like this. I'm going to have MC VC over MC plus 1/5 MC. And that's going to be equal to VF. Now, I can leave my answer like this, but I can also do some algebra to end up with a simplified answer, which will help me in the next part of the question. So if I do my algebra, I'm not going to do it right here because I want to keep this video short. I end up with 5/6 VC equals VF. So this part of the equation is telling me that I end up with a smaller velocity at the end than I started with. So this is my answer to part A2. So let's look at part A3. Derive an expression for the change in the kinetic energy, delta K, in the block cart system from t equals 0 to t equals t2 in terms of MC, VC, and physical constants. Begin your derivation by writing a fundamental. So I'm going to use this. I'm going to save this for later. So I'm going to write this up here. 5 over 6 VC equals VF. And I want to find an expression for the kinetic energy. So I know that the change in kinetic energy is going to be equal to the final kinetic energy minus the initial kinetic energy. And I know that the final kinetic energy is going to be, well, the equation for kinetic energy is 1/2 mv squared. And if you don't know that off the top of your head, it's helpful. I would encourage you to commit that to memory. So I have 1/2, my final mass at the end is going to be 6 over 5 mc. How did I get that? Well, I just added the mass of the cart plus the mass of the block that falls down on top of it. And now I have my final velocity, which I found before. It's 5, 6 VC. This is squared. And now I'm going to subtract. I have 1/2 mc VC squared. This is my term for my initial kinetic energy right here. And so now I have to do some algebra and simplify this all the way down. I'm not sure if this would earn credit. I don't know what the scoring guidelines are for this test yet, but we're going to go ahead and simplify it. But if you're not sure about simplifying, if you're worried you're going to make a mistake, usually this will get some sort of credit. You maybe only miss a point for not simplifying it. Okay, so let's simplify this here. So if I square this term right here, I end up with 25 over 36 VC times 6 over 5 MC times 1/2. And this is all going to be minus, this should be VC squared. And then I have 1/2 MCVC squared. And so now I end up, I'm going to end up canceling out these two terms right here. This cancels out with this, and I end up with a 5 on top, and this cancels out with this, and I end up with a 6 on the bottom. And so I end up with 5 over 6 times 1/2, which is going to be 5 over 12. So I end up with 5 over 12 V MCVC squared. My MC didn't go anywhere. Minus 1/2 MCVC squared. And so my final answer, despite me running out of space here, my final answer is going to be negative 1 over 12 MCVC squared. And so that means that my change in kinetic energy is negative 1/2 1/12 MCVC squared. So which means that the kinetic energy has decreased from the beginning to the end. So I've lost kinetic, well, I haven't lost kinetic energy, but kinetic energy was not conserved throughout this collision. So this would be my answer for my second part right there, part 3. So now I'm going to go on to my final part right here. So it says consider the case when a new block is dropped and collides with the cart. The new block slides along the cart during the collision but does not slide off the cart. Time interval when the new block collides with the cart and moves together with the cart is delta t. During delta t, there is a frictional force between the new block and the cart. Indicate whether the x component of the momentum of the new block cart system increases, decreases, or remains constant during delta t. Justify your response. So the key fact that you're being asked about in this question is, does the momentum change because of this cart that it now has, it's sliding around with friction on this surface. So over here, this block this block is now sliding around with friction on my cart. So it's no longer a friction. It's no longer a collision where the block remains stationary on the surface. It's sliding around and there's some friction there. So consider the case when the new block is dropped and collides. Indicate whether the x component of the momentum increases, decreases, or remains the same. Well, there's a force of friction. There's a force of friction. This would be the block on the cart. And then in the opposite direction, there's a force of the cart on the block. But these two forces in my cart block system are internal to the system. So they're not going to change my my momentum because they're internal forces. So it remains constant. It remains constant, and the reason why is there's no net external force. No net external force. Whoa. There's no net external force. Those two forces are internal to the system in the horizontal direction. I'll just say in the x direction. And so because there's no net external force in the horizontal direction, the momentum of the cart block system is constant. So P is constant. The momentum does not change.